Hello, in this video I'm going to talk about mean drift velocity. So this is the answer to the question of how fast are electrons moving along a wire when we've got a current flowing in it. So this is the average velocity of an electron moving along a current carrying wire. Now I've been saying quite a lot in the previous videos that electrons don't move very quickly when we've got a current flowing. The point of the electrons moving is the movement of the electron propagates the electromagnetic field along the wire, and that propagation of the field happens very, very quickly, and that is what's carrying the energy. That's what's carrying the potential energy, our electrical energy along the wire. So it's useful to be able to quantify to some degree, well, how quickly are these electrons moving on average? So hence mean drift velocity, mean for the average drift because it's going very quickly, and then velocity because we're looking at velocities. So let's start simple then and say we've got a constant direct current. So let's look at that and we say, okay, well, our current, this is our rate of flow of charge. So that's going to be an amount of charge, delta Q, that's passing a point in the circuit in some time delta T. So what do we mean by this? Say we've got a wire, we've got our point in the circuit here, whatever, some point X, and we've got the electrons are moving left to right, so we've got our conventional current going the other way, and we've got some volume here of the wire. We've got a cross section of the wire, cross-sectional area A, and some length here, L. This volume has passed point X in some amount of time T. So in time T, this volume, this shaded volume, all the electrons in there have gone past point X. Right, so now we can turn this into an equation here for I. Right, so in that amount of time, I mean, we're fine for delta T because that's just going to be equal to our time T. We're saying it's taken time T for everything to move past the point. So that's fine. But how much charge have we got? If we want to get how much charge we've got, we need to know how many electrons. So we need a number of electrons, and we need to multiply that by our charge on the electron. So charge on the electron, that's fine. How are we going to get number of electrons? Well, we're going to need a number density, which we're going to call N. So that's our number density of electrons. Number density of electrons. So that is this is number of electrons per meter cube. Per meter cubed. Then we need the volume because that's going to give us the meter cubed. If we multiply N and V together, we're just going to be left with a number of electrons. So what is our volume? Well, that's our cross-sectional area times the length. So we just need to put all of this together, which gives us that delta Q is going to be equal to our volume, A times L, multiplied by our number density, which is N, and then multiplied by the charge on the electron, which is an E. Then we need to divide this by delta T, which is just T. So we've now got a nice equation for our current. Now, the extra step, because you'll notice we haven't got velocity in here at the moment, is, of course, this distance. The electrons are just moving along here, along the wire, and they've moved a distance L in times T. So distance over time is giving us our velocity, which is what we've got, L over T, in this equation. So it gives us a final formula for this of saying I equals A N E V. Now, this is all great, but it does kind of rely on knowing a lot of things. I mean, if someone derived this equation back in the 18th century or something like that, well, this isn't a done deal. You're not home and hosed on this because there's loads of stuff that you don't know in all of this. So A is fine because we just get a ruler out and we can work out our cross-sectional area to a decent degree, or get a micrometer out or something like that. We're quite adept at measuring length. So cross-sectional area, not really a problem. But we've got problems with the rest of it. If we rearrange this and we want to work out what V is, and I'll do an example of that in a minute, we need to know what the current is. Okay, A is fine. We need to know a number density and we need to know the charge on the electron. So this kind of historically, this is built up over time. The early definitions of current, when they were saying, well, what is 1 amp? If we need to give an actual definition of what an ampere is, and back in the day, everything was empirically based. They tried to move away from that with the reclassification of the SI units. It was about 5 years ago, or whenever it was, I think it's 2019, where they defined a whole load of constants and then defined all the units off of those constants, trying to get it away from the variability of empirical measurements and such like. But back in the day, they weren't doing anything like that. So you have to start off by saying, well, what is an ampere then? And they were looking at, well, what is the force generated between two current carrying wires? You set up two wires carrying current, and then it ends up that, and you put them a certain distance apart, and then you'll say, okay, well, what force have we got that's either repelling or attracting these wires, depending on the direction of the currents? So at least that's some way of saying, okay, we now know how to measure current, but that's still a starting point that you have to do experimentally to come up with that. But you think, okay, we've now got a tick there for I, we've got a tick for A. Now we're, well, how are we going to get N and E? I mean, we know that working out the charge on an electron, our basic building block of electric charge, that wasn't until 1910 when you had the Millikan oil drop experiment. So you've got to go out now and do the Millikan oil drop experiment, and that give you a value for E, the one that we use without a second thought, really, but it's only been around for just over a century. Then you need to go and get N. I mean, that's easier said than done, to get a number density for a particular material. So you've got to go through a whole number of things here to get a number density, because you're trying to work out, well, how many free electrons are we going to get per atom, depending on what we've made the wire out of. So essentially, you're looking at the valence of the element that you've made the wire out of. So that requires knowledge of the periodic table. Then you've got to work out your density. So you've got some way of saying how many atoms there are in per unit volume of the wire. Then you need Avogadro's constant, which again comes really from the Millikan experiment, because that allowed people to solve the charge per mole of a substance. Faraday, back in the early 19th century, in his work in electrolysis, he did a lot of work in chemistry, and in electrolysis he was able to work out the charge per mole for certain substances. But until you know the basic building block of charge, until you've got the charge on an electron, you can't work out Avogadro's constant. So the long and the short of it is, there's still a lot of work you've got to do, historically speaking, in order to be able to use this equation. Now, I mean, nowadays we've got ways of measuring current. We've got well calibrated ammeters. It's very easy to work out A with micrometers and well constructed wires. We've got tables of data for number density of electrons for different materials, and the value of the charge on the electron has been well established for a century or more. So it's simple now, but I'm just trying to get the point that it wasn't simple from a the perspective of science through history. Anyway, having laboured that point maybe a little bit more than I needed to, let's now get a value then for V. Let's take some typical values. Let's say we've got a 1 amp current flowing through a 0.1 millimeter wire, diameter that is, so that's the diameter of our wire. 1 amp flowing through that. It's made of copper. So let's have that. We can look up on our table and see that copper has got a number density of 8.5 times 10 to the 28 per meter cubed. So that's a lot of electrons waiting there to get going, which is what you'd expect in something that conducts as well as copper. So now we have to put all this into our formula here to get that V is going to be 1 over. So let's just stick this in brackets and do a reciprocal. We've got our cross-sectional area, so we've got to do a pi r squared on that. So we're going to be doing pi times 5 times 10 to, what's that, minus 4 squared for the radius. So that's our pi r squared, that's our A. Then we need to multiply by n, which is 8.5 times 10 to the 28. Then we need to multiply by E, which is our 1.6 times 10 to the minus 19. And then we need to take the reciprocal of all of that. So tapping all of that into the calculator is giving 9.3 times 10 to the minus 5 meters per second. So we're somewhere in the order of 0.1 millimeters per second. That is not a lot. It really is not a lot. We can see what sort of things are going to change this. If you've got that copper wire, well, N and E aren't changing because it's still copper, so N doesn't change and E is E, so that's fine. If you change A for the same current, so if you take a wide bit of wire, put it in series with a narrow bit of wire, so we must have constant current because of Kirchhoff's first law, nothing's changing there. So if you narrow the wire, then the velocity goes up. If you widen the wire, then the velocity goes down. It kind of makes sense. You've got fewer electrons in a certain length of wire if it narrows, so you have to push them quicker in order to get the same amount of charge passing a point in the circuit, which is what we need for constant current. So yeah, your velocity changes depending upon the cross-sectional area of the wire, all other things being equal. But this is the idea of the mean drift velocity. I mean, not all of the electrons are going to be moving at exactly the same velocity. They're going to be collisions and such like that are happening inside complicated structure of the wire. But overall, I mean, you can see how many electrons there are. I mean, we've got 10 to the 28. I know meter cubed is a lot bigger than you're ever going to get for a wire. But there's a lot of electrons around. So having a variation, averaging them out is, fine. You're still going to be getting the same amount of charge passing through a particular point to keep that constant current. So yeah, I just wanted to run through that because it is something that comes up a lot, just to embed that understanding of what's actually happening when you've got a current flowing along a wire. I mean, this is just ramming home that the electrons don't move quickly, but when they do move, you get speed of light propagation of the field, and that's what's taking the energy with it. So it's a very important distinction in understanding electricity.